Hi, welcome to 10th live session of Points of Topology to NPTEL course. This is Shovik and I'm working on sparseling my data and this is my I'm a PSS. Before starting, let me know am I audible and the screen and is the screen visible to you?
Yes, yes.
Okay, thank you, Mr. Okay, so before starting, do let me know do you have any question or any um, doubt? If not, then we shall move for the next solving other assignments. Let me know do you have any question or doubt. Mustafa, do let me know. Okay, okay. So let's start the session. Okay. So today we shall so in last live session we have gone through um, assignment 5 and assignment 3. Today we shall start with assignment 2. Assignment 2. First we start with the objective as of part. Okay. So let me um, write down the questions here. Okay. So suppose so first question is the following. Suppose let here R3 to R be a C1 function and suppose B is equal to x0, y0, z0 such that f of x0, y0 is equal to 0 and then consider the statement. The statement S is given by there exists B greater than 0 and unique C1 function g from B so y not to R such that g of x naught 1 and z naught and f of x comma y comma gxy is equal to 0. Now the question is the following. State whether the statement S is true or false in these the following cases. Firstly, f of x y z given x squared plus y squared plus 2z squared b is equal to 1 1 1. Option B, f of x y z equal to 2x squared minus y squared minus z squared b is equal to point b is equal to 1 1 1. And option C is equal to f of x y z equal to x squared plus y squared minus z squared b is equal to 0 0 0. Okay. Now the question is that on which of the functions will satisfy the statement S. Okay. So basically, what is the question is given? The question is that so we have the function from R3 to R, and C1 function is the point order at the point 0. And suppose this statement is such that here is just a p greater than 0, and unique continuous function g around the ball of x naught y naught not 2 real line whose image is real line serves the g of x naught y naught is f naught f of x y comma g of x y equals 0. State whether this statement is true on which of the following cases. Okay. So for this, what is the interesting thing? It is that main technique is that we need to somehow decode the implicit somehow need to decode the implicit function here. So let me so let me write down solution. This function will satisfy the function given in B will satisfy the function given in C will not satisfy. How to prove it? So the function h of xy for the point A, h of xy is x square y square. This takes value 2 at x comma y is equal to 1 comma 1. Okay, so we can choose row greater than 0 so that h is positive in 0 1 comma 1 and put z equal to g of x comma y is equal to over h of x comma y. Okay, and which is uh, a smooth function in 0 1 comma 1. It follows that f of x comma y comma g of x comma y is 0. And option B is same argument as in A. Okay, same argument as in A. And option C is so if we do g of x y equals plus minus over x square plus y square, which is of course continuous, but not C1 in any neighborhood of 0 comma 0. Okay, so that's why this is the whole argument. So first what we took h of x as x. This function takes the value at 2, so we can choose to go greater than 0 due to continuity and positiveness of h. Okay, and we follow same argument, but fortunately if we take gx equal to x y squared, so of course this is not satisfied. This given in this condition in any neighborhood of 0 0. That's why this is not true. Okay, 1 minute. Okay, now let me check your one. Okay, so now the next question. The next question is true or false. Okay, compact subsets of a topological space are always closed. Think about how to do. Compact subset topology are always closed. We know that in a house job it is true, but this is not in general. So try to think out a counter example. Try to think about counter example. Please think about ISO bag for 2 minutes. How well? Well, so of course the answer is false. So how to do? Observe that singleton sets are always compact, but not necessarily close the future. So that's right. So for the for what you can do, you can consider uh, inductive topology. So there you can consider singleton always compact, but singleton is not closed in inductive topology. Okay, because in inductive topology, the only set which closes either the whole set or the empty set. Okay, okay. This is option. This is now question three. Question three is which of the following true for Q with usual topology? If the following are true for q is the one. Oh well. So so the question is which of the following are usual topology? First option is locally comp. Option B is Hausdorff space. Option C second category space. Option D normal space. Okay. So which one will sorry which one will satisfy usual topology? Solution is B and D. Now one must one. So look. So take Q is equal to union n un where Qn is an enumeration of Q. Now each Fn is a closed set with empty interior. So Q is not second category. Now being Hausdorff, it is not locally compact. Else it will contradict uh, well-known theorem. What is that? Think about it. Try to identify which theorem it will not, which theorem it will contradict. So, so what is the technique? The first, we need to consider the enumeration of Q. Okay. Now, for each Fn here, close entry interval of Q is not state that. Now, being housed up, it is not locally compact. Else, it will contradict. Important. Question of which is that? Think about it and let me know. You can let me know in the email or let me know in the next live session also. Okay? Think about it. So this theorem is actually very famous and quite important, and people often use it while solve problem. Okay, and an exam point of view, this theorem is quite important. Also, okay, so do think and do let me know in the next session or through by email. Okay, so now the next question. Let x 0, 1, 2, dot 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 is equal to n union 0 with topology generated by the curve-based 0, comma and then x is up. local compact space P1 space options compact space option D Lindelof space. Okay, think about it and do a little bit of history. Values of x we have discrete points with the topology generated by 0 comma n. At a subspace. Now the question is x local compact T1 compact. Which one is true? Yeah. So now the solution is option. Now question is how it's possible. Um, First observe that the option A is false. Why? Since for the element 1 belongs to X. For the element 1 belongs to the open set 0 comma 1 containing it, there exists no subset V of 0 comma 1 containing 1 for which V closure will be subset of 0 comma 1. Okay. Now because singleton 1 is not open and closure of doubleton 0 comma 1 contains all of it. So look, sorry. So this option A is false since if you consider element 1 belongs to X and consider open the doubleton 0 comma 1, then there is no open set V containing 1. Okay. For which V close subset of open 0 1. Now since singleton was not open, the closure of 0 1 contains the whole option. Okay. And for why option B is not true is false since there does not exist open subset of X containing 1 that does not contain option C is False. Why? Because the open cover because the open cover doubleton 0 comma n belongs to n, does not have a finite subcover. Option D. Why is true? This is true as the set X is counter. Oh, now, now let's get to the question of five. One minute. Oh, before going to question of five, let me know if there any question or any doubt.
Can you repeat the second question?
Okay. So,
Because
okay. So your doubt is clear.
actually give some example. Okay.
Uh, so, um, so, um, so well, one minute. So we have seen that compact plus house dot implies closed. That is, if a given set is compact and the mother space is house drop, then the compact set is always closed. And if you look into the proof, then compactness, then the house dropness was actually we are using in the proof. So of course, if it is in a house drop, the compact does not necessarily imply that it's closed. So that's why you need to provide a counterexample. One possible very good counterexample is the following. Namely, consider X with in discrete topology and consider the open sets are phi comma x and as well as the closed sets are phi comma x. Now, of course, if you consider singleton set, this is always compact in X. Of course, but singleton set is not closed because in discrete topology means the open sets are only phi comma phi and the whole space. So the closed sets are only the empty set and the full space. So singleton set cannot be closed in the indiscrete topology. Okay, so that's why the singleton is compact but not closed. That's why it's an counterexample of the question number two. Do you understand, Mr.?
Yes, yes.
Okay. Do you have any more questions?
No,
Okay,
please
thank you.
continue.
Okay, so now let's. Okay, so till now, what I've discussed, please go through it. I shall be back after 2 minutes. So well, so now let's go with the question number what? Question number five. Okay, so true or false? Okay, every closed set G delta in a compact Hausdorff space is precise zero set of a continuous function. Every closed set G delta is a compact Hausdorff space in a compact house with a precise zero set of continuous function. This means what? We need to construct a function which is real valued over a compact set such that it's such that the point in which the function becomes zero is a G delta set. Okay. So of course this problem is quite uh, unpredictable. For that you need to practice more and more. Okay? So let me write down the solution for you. So of course it is true. Okay. Now let A is equal to intersection even be the closed G delta set. Okay. In a compact house space. Okay. X. Now compact and house space are normal. So X is a normal space. Now using Euclidean's lemma, there is a function fn from x to 0 1 such that fn x equal to 0 on f and fn x is equal to 1 on un complement. This implies what? This implies that there is a function if we call it f of x is equal to summation and fn by 2 to the power n is the required function. So let me uh, 1 minute. So So we have some A that is suppose the G delta set that is A is the countable union of countable intersection of open set be a closed G delta set of compact Hausdorff space. Now compact Hausdorff normal. So X is a normal space. Now using Euclidean's lemma, there is a function fn from x to 0 1, so the fn x equal to 0 on x and fn x equal to 1 on even complement. So then fx equal to summation fn by 2 to 1 is a required function. Okay. So now so now go to the next question. Question is so okay. So this question contains some new thing known as topological group. Okay. I mean, so so basically it has a group structure and it has a topology on it. Now the point is that topological group is means a group which is a topological space along with the fact that the group structure respects the topology. This means so basically the point is that the group operations, namely the multiplication and the inverse, these two operations continuous operations. Okay, this will be a topological group. Okay. So let's G be a topological group and let X be a topological space. So you have seen that so you have seen in the abstract algebra the concept of action of a group on a set. Okay. Now same thing here. Here the topological group acting in a topological space. Okay. And so it's an so is a continuous map where from G cross X to X, G X goes to G dot X. Such that the following will happen. G dot H dot X equal to G H dot X option B E dot X equal to X for all X equals to X. And GH belongs to G. And definition 2 is the following. Definition 2 is the let G be a topological group act on a topological space when we say G acts on intransitively if for every xy belongs to x, here exists G belongs to G such that Gx equal to y. Okay, and the definition 3 is the following. Let x belongs to x, then that's the hx is equal to all those G belongs to G such Gx equal to x is defined as isotropy subgroup of X. Okay, one minute. So these are the total three definitions till now. So first one was the action. Second definition tells that what does it transfer the same as in the algebra. And third one is the isotropy subgroup that we have the same as seen in the algebra group action. Okay. So please go through definition once and let me check that what next question I should put. Kindly give me 2-3 minutes. Sorry for the confidence. Please go through the examples and try to understand how these are same as in the abstract algebra definitions. So now, so now, based on this, there is the following theorem, namely, so theorem goes let G be locally compact Hausdorff and Lindelof space acting transitively on a locally compact Hausdorff space X, then G by H is homeomorphic with X, where H is isotropy of some point. Yes, this one is what. So this tells that suppose G is a locally compact Hausdorff Lindelof topological group acting transitively and locally compact Hausdorff space, then the space can be thought as a quotient of G via some isotropic subgroup at some point. Okay, so yeah, it's a very powerful theory. Of course, as you can see that the given space can recover directly itself from the statement. There is some action. That's all. Even the action is not important. Only the statement is the fact that there is some action. That's the necessary thing of for recovering our X. Okay. So of course, this theorem is like coherent of the crown. Okay. So now let's try to prove it. This proof goes as follows. First, using Beer category theorem, one of G and K dot X has non-empty interiors. An interior of K inverse AX is equal to K square dot X equal to B dot X. And this completes the proof. This completes the proof. For second point, what it do? Let B be an open vertex. Subset of G. Now since G is locally compact, and Hausdorff space, so there exists a neighborhood O of E such that K is equal to O. Okay. Huh. So, so V is the open subset of G. Now, since G is locally compact, a house drop, so their neighborhood G of E is such that K is equal to 0. Closure, of course, is compact. And K is equal to K inverse and K square subset. Okay. Now, part C is what I need to prove. One, to prove the map phi is an open map. For that, what you need to do? For that, you need to use what you need to use Lindelof method. Here exists G1, G2 such that G is equal to union G and O. This is equal to union N, G and K. Okay. Now, this does that since phi is a continuous bijection, so we only need to show phi is an open map. Yes. Since U is open subset of G and G belongs to U, we need to show psi G is equal to G dot X, which is in the interior psi U is equal to U dot X. Okay. This gives X equal to union N G and K dot X using transitivity of action. X, G and K dot X is compact and hence closed since X is household. H. Consider the following diagram. G to G by H, 2 F C and 2 from P. Okay. Now in this diagram, this pi G is equal to GH and she of G of H is equal to G dot H. And psi G is equal to Gx for all G belongs to G. And this diagram comments. And final step is the following. Since G inverse is a homeomorphism, it is equivalent to prove that X is in interior of G inverse U of X, where G inverse U is a neighborhood of P. One. One. So her EG inverse is a neighborhood of E. So, or equivalently, need to prove that when P is a neighborhood of E, X belongs to interior of X. So now the question is that observe that if we go to the states, go to H, to E, to C, to F, to I, to uh, B, to D, to A, then this proof will complete. So let me rediscuss the whole proof because this proof is quite long. Okay. Well, so the thing is, so suppose this is a topological group. Okay, topological group is a group which is a topological space along which has a group structure, and the group structure respects the topology and vice versa. That is the composition map and the universal continuous. Okay. Now, so there, so like abstract algebra, here is also the notion of action with topological group, topological space. So the G, so that which is, those are the action properties. And the next thing is that G is a topological group. Then the actions of the transitive if we take any 2 points x and y from the x capital A, from the space capital X, then x can be obtained from y by action of some element. That is, there exists a G belongs to G, so the Gx equal to x. Okay. Now definition. let X belongs to X. The isotropic subgroup, we mean all those G in G, since Gx equal to those G which fixes X. Okay, the isotropic subgroup. Now theory is the following. Suppose G is a locally compact Hausdorff Lindelof space acting transitively on a locally compact Hausdorff space, the G by X is a homeomorphic to X. And where G is the isotropic subgroup at some point. So this is possibly the very big theory, very big achievement in the early 80s. Okay, because these all things are very old, and so yeah. Now, now using Beer category theorem, GNK dot X has a non-named interior. Okay, has a non-named interior of so that K inverse Kx subset of Kx correct subset of Bx, and this is the proof. Okay. Next, so suppose we is the open subset of G. Now since G is 1 minute, let me check everything was fine or not. Now, since G is locally compact Hausdorff space, so there exists a neighborhood 0 of each of the K is equal to 0 prime is compact. Okay. Want to prove the Scheider open map. For that, what we need to use the Lindelof names of G. So there exists G1, G2 such that G is equal to union of G and O, which is equal to union of G and K. Now, since phi is a continuous bijection, so we only need to show phi is an open map. Now, since there is an open subset of G and G belongs to U, we need to show phi G is equal to Gx. The interior of phi G is equal to U. This gives that X equal to union of Gn, where each Gn is compact and hence and closed. Now consider the following diagram. G to X and G to Gx. Now phi of G is equal to Gx and phi of G is equal to Gx. Now these diagonal comments. Since G inverse is homeomorphism, so it is natural to prove that X is the interior point of G inverse of X. But G inverse of X is a neighborhood of X. You need to prove that V is the neighborhood of X. So then X belongs interior of V dot X. Okay. So that is the argument. Okay. Now, okay. So do let me know till now. Do you have any questions? As I'll wait for 2-3 minutes. Do let me know. Do you have any more questions from this objective part? If not, then we can move on to the subjective assignment.
Can you again explain the isotropy subgroup?
Oh, what?
Actually, we know isotropy subgroup.
Sorry, please repeat it again. Mustaq, please repeat again.
Isotropy subgroup.
Okay, okay. So, isotropy subgroup, one minute. So, the definition is here. So, suppose X is an element in X, then the one. Suppose X is an element of X, then the all those G inside G such as Gx equal to X, then all those G which fixes X is a subgroup of X, and this subgroup is called isotropy subgroup. Okay, so this means what? Any element outside the isotropy subgroup will not fix G. So this is kind of fixes point set for each of the points. So this is the basically isotropy subgroup. Okay, that's all. Any questions? Any more questions?
No, we got
Oh, okay. So Mustaq, now let's get into the subjective assignment part. Well, so now let's get into the subjective portion. Assignment 2, subjective assignment. Okay. So, one minute. So let me check the assignment. Wait a minute, please. So let me think what could. Huh. So so definition for a topological space. A topological space is called a sequential space. Sequential space if it satisfies the following property. A subset of X is open if and only if every sequence in X which converging to some point A is eventually inside A. A topological space is called a sequential space if satisfies the following property. A subset of X is open if and only every sequence S in X is converged some point is eventually inside A. Okay. Now the question is that show that a sequential space X which is Hausdorff belongs to C object, that is X is compactly generated. Compactly generated means X can be written as union of compact sets. So this is what we mean by compact generated. So, a topological or sequential space has a following property. Suppose A subset is open if every sequence which converges some point in is eventual inside it. Show that a sequential space X which a house drop belongs to compactly that X is compactly general space. How to solve this? Suppose not. Then here is a subset Fx which is closed in case but not in X and put U is equal to X minus X which is not open in X. Now since X is sequential, so this means there exists a sequence S in X which converges to a point in yes belongs to U, but yet the sequence is not eventually in U. This means there is a subsequence S in K inside F, and clearly this subsequence converges to X. Now put S equal to S in K, K greater than equal to 1. Then K is compact subset of X, and so therefore K intersection S is closed in X. Well, and this is not possible, and this means yes belongs to A, which is absurd. So let me get in whole argument. So what we so we have a, so what we need to show the space is sequential space which is also housed over space that's another compactly generated. This means what? This means that set the space can written as union of compact spaces. countable in a compact space. So if not, suppose it's not compact, this is what? During subset F, so there is a subset F of X which is closed in Kx, but not in X. Now put U is equal to F complement, which is not open yet. Now since X is sequential compact, this means there exists a sequence X and X which converges to a point in X belongs to. And now get the sequence which is not eventually in U. This means that there exists a subsequence X and K inside F. Clearly, this subsequence converges to S. Now put K is equal to singleton S equal to union of X and K. Then K is compact subset of X. So K intersection F is closed in K. This means S belongs to. This is absurd. Okay? So that's why this is not possible. Well, so now the next question. Does there exist a non-compact topological space with a with a compact dense subset? Does there is non-compact topology the compact? And think about it, and think about I said back in a few minutes. Well, so uh, so the question is that, sorry. So the question is that, does there exist a non-compact topological space with a compact having a compact dense subset of it? Now, how to reach? So the answer is yes. And how to do it? Now consider the following example. Consider x is equal to 0, 1, 2, dot, 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 which is nothing but the natural number similar to 0, and with topology generated by the subbase 0, n. N belongs to n. Then x is not compact as the open cover double on 0, n. This does not admit a finite subcover. And however, singleton 0 is a dense subset of X, and it is compact as well. However, the singleton 0 dense subset of X is compact as well. So, so thing is that the answer given question that there exists a non-compact logicals with a compact dense subset. It is true. Take x to be 0, 1, 2, dot, dot, dot. With the topology generated by the subbase 0, n, x is not compact. The open cover 0, n does not have a finite subcover. However, 0 is a dense subset of x and it's compact as well. Okay. So now the next question. Let x be pseudo-metric space with compact dense subspace. Sorry. Let X be a pseudo-metric space. Show that every closed subset in it is a G delta set. Okay. How to prove it? Well, this proof is not somehow obvious. It is not somehow obvious. Think about it to let me know how you can approach. Okay. So let if we so in order to show something, what we need to show that that set can be written as intersection of closed sets. So that suppose if it's a closed set in x with tau d, and consider the function e of x to r given by x goes to d of x. First, we observe that f is upper semi-continuous. Upper semi-continuous means that fx that 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 from 0 to x plus epsilon, that condition will only satisfy this is upper semi-continuous. Okay. So this can be done in the this can be done different way. So this can be done as follows. So of course, one way is to go directly to the elementary method, and other way is that observe that each function y equals to dfy is upper semi-continuous on x comma tau d, and if being the infimum is upper semi-continuous. Therefore, un of x belongs to x as the dfx less than 1 by n is open for every f. Now we claim that f is equal to intersection un. LHS subset of RHS is obvious. How? Think about it. Let me think about the next question. You please think about how to prove the claim. So, in order to prove the above claim, so we need to use the following technique. So suppose R belongs to X belongs to RH. So this implies what? D of fx equal to 0. This implies what? X belongs to F closure. This is equal to F belongs to X closure. Okay. So basically, and how this is coming? So basically, by definition of what? Of infimum, for every n belongs to n, here xn belongs to f, so the g of xn comma x, this is less than 1 by n. So this says that the sequence xn goes to n, x belongs to f closure, which is equal to f. So the full argument. So let me repeat the full argument. Well, so suppose x is pseudometry space. What do we need to show in every closed set? The G delta set. Wait a minute, please. So basically what we are doing is that suppose it is a closed set in x tau and f x2 bar your function. Suppose x goes to d of it, then f is upper semicontinuous. This tells that y goes to d of y equals upper semicontinuous, okay, on x comma d tau of being the infimum. So therefore the even x belongs to a dfx is 1 minus open for every x. Now claim is that f is intersection even, okay. Now this says that RHS subs LHS or RHS object. Now for the reverse, what do you do? Suppose X is the element of RHS. So DFX equal to this implies what? The
Hello?
yeah, Mustafa, tell me.
Can you repeat the second one?
Yeah, okay. So okay, so let me finish this. So we have some DFX equal to 0. Okay, this implies what? By definition in infimum, we can get a sequence xn, so the d of xn comma, kindly hold a minute. Hello, hello. Yes, tell me. Ah, sorry. Okay, okay. So basically, what we're saying is that there is no right answer, right? So what we're saying is that basically there is no right answer, right? Okay, okay. So one right is fine. Okay, so no problem. Just put a extra amount of period, no problem. You can put extra amount of little extra amount of period, no problem. That will be fine, but it will be better if you can give some extra amount of period. That will be better for me. So I'll. Yeah, contact number is 755 Yes, 755 Okay. Or there is other than raita, I have ordered some masala kind of thing, right? Yeah, other than raita, there is some masala kind of thing, right? I have ordered. Yes, yes. So if one writer is not available, so you can put extra salad or you can give extra beer. No problem. Yes, yes, that's fine. Thank you. Oh, so sorry for the inconvenience. Okay. So by definition, infimum for all n belongs to there exists a so the okay. So now okay. So this question is solved. Now let's go to the Musta's question. So Musta, can you please repeat your question or which question number are you asking? Musta, can you please repeat your question? Hello, Musta, can you please repeat your question? Okay. So now let's go to the next problem, namely what? So prove that every non-empty open subset U of a Baire space X is a Baire space. So how to solve it? Suppose for each n belongs to n, we are given On, which is open to U and then to U. The state when prime is equal to On union X minus U closure is open in X and dense in X. Okay. Now, since X is a Baire space, so intersection N when dash is equal to intersection N On union X minus U closure, which is nothing but intersection N On union X minus U closure. This is dense in X. So therefore, U should meet intersection N when prime, and since it does not meet X minus U closure, it must meet intersection even when, and this means intersection N or N is dense. Okay. So let me repeat the argument again here. So the what we need to show, we need to show every non-empty set in a Baire space is a Baire space. How to prove it?
Can you repeat this one once again?
Yeah, sure. So So the question is to show that every non-empty open set U of Beer space is a Beer space. Okay. So for this, what we need to do? So choose an open set ON in U, which is dense in U. Okay, and set ON prime is equal to ON intersection x minus U closure. This is open and dense index. Now since x is a Beer space, so intersection of ON prime is equal to intersection of ON union x minus U closure. This is equal to intersection ON union x minus U closure is dense. So U should meet intersection ON prime. Since it does not meet x minus U closure, so it must meet intersection ON. And this means that intersection ON is dense in U. Okay. So Muktab, do you so you were asking some other question few minutes back. So can you please tell which question it was so that I can discuss?
No, I am asking this one.
Oh, so okay, okay. So well, so now so this is the finishing of the assignment to subjective. Now let me 1 minute please. Okay, now few times left. They are higher. So let me introduce a notion called as manifold. So for those who uh, is it not working? Yeah. For them who shall work in topology or who shall continue in this particular subject study, they will encounter an object in topology named as a manifold. Okay, this object is the fundamental importance topology, and point is that whatever you look inside the nature, whatever the object shape in is available in nature, everything is nothing but almost a manifold. Okay, for example, okay, so let me give some definition why I'm saying so. So suppose what is the manifold? Manifold is a Hausdorff space, okay, which is second countable, and so that if we take any open set, then around the open set we can get a ball. I mean, we can get a neighborhood which is diffeomorphic, sorry, which is homeomorphic to usual standard Euclidean ball. Okay, so so now if we look at the nature, suppose you look into the you suppose you look into a stone. So basically, stone, of course, is I mean, everything since we are living inside Earth, so here everything is housed up space, okay? And suppose if you take in a point of the stone, if we consider an open wall around the stone, so how that will look like? So in an open wall will look like this, right? And this is nothing but usual open wall homeomorphic, correct? Suppose if you look at the paper weight, if you look at bottle, everything will satisfy the same property, okay? So that's why the starter of manifold is a fundamental interest in topology, not only in topology, in the geometry also. Okay. So let me introduce the notion of it. So wait a minute, please. Hmm. Okay. So definition. Let X be a topological space will be called a manifold if X is second countable plus Hausdorff and If we take any point in X, there exists a neighborhood U of X, thus that U is homeomorphic to standard ball in Rn, that is Bn01, and then X will be said and manifold of dimension n. Dimension of X equal to n, okay. So it is a manifold, okay. And till now there is nothing complicated here. Wait a minute. Wait a minute, please. So, so for example, consider the standard sphere. All those x belongs to Rn plus 1, so the norm x equal to 1, okay. So leave it. Consider n equal to 2, that is usual standard sphere, okay. Of course, usual standard sphere is a compact Hausdorff space, space, and of course it is also second countable, so of course second countable, okay. And there is no confusion on that. Now we need to show that our usual condition will work. That is, if we take a point around X that will homeomorphic to an open ball. Okay, how to do? So this sphere can be thought as follows. Sphere can be thought as union of this plus this, correct? Now consider this thing. If we pushing up this, then this will look like this skin wherein a 2, and similarly this also. So that is, if we consider sphere, then each of the hemisphere we can think about standard disk, I mean homeomorphic standard disk in R3. Okay. So now if we consider the open portion of it, then that will homeomorphic to open ball in R3. Okay. So that is the argument. Okay. Candidate. So now, of course, if we consider Rn, so of course R2, R3, these are manifold, of course. Okay. So sphere, Sn, Rn, all are manifold. and of course any open ball is also a manifold one. So any open ball is also a manifold. Okay. So not only that, I mean, so now the point is that there are many observation one can find with respect to manifold, which we shall in the next live session. Um, so today we have discussed about some basics of manifold finally and discuss two assignments. So in the next live session we can continue by discussing from manifold. Okay. So let's stop here. If you have any question and any doubt, you can ask in the next live session. Okay, or you can drop an email. I will reply. Okay. So let's end here. Thank you for attending the session. We shall meet on the next Friday. Okay. Thank you. I'm leaving the session.